Recording is rolling. It's Tuesday, February 10th. So we're starting on the very last AP topic, Unit 8. The fluid dynamics. I'll point out the last set of formulas to you guys, which are right here. And the above is right here. So we'll talk about pressure, what is pressure, and how does that relate to fluids. Talk about these principles, Pascal's principle, Archimedes' principle, and then there's conservation of flow that leads also to Bernoulli principle. Guys, your next AP classroom is open. It's Unit 8. This the multiple choice questions. And so right now, I tentatively have this due 1 week from now on Tuesday. That's the earliest I would go over that with you guys. I might have bumped that back a day, but we'll see. Guys, you guys are gonna come to school this coming Monday, right? Because President's Day. Right. So. All right, so yeah, so I won't see you guys Monday. Great. And then right, so you guys got this in your planners. So go ahead to that. I'll see you by the end of the week if you guys have stuff. You'll be able to answer those questions over the weekend. Right. All right, so great. Here's the last set of AP formulas right here. Right here.
You gotta hang out at your house while you're.
All right, so these I'm circling right here, and I'm gonna go through my posters for you guys, and you guys get some larger versions of these. I have orange banners, so
That happened to me like
hashes an orange right here.
You're like,
And these are fluids. Right, so all those right there. All right, okay, you know what? Let's get a close look at some of these. Okay, guys, see that Greek letter right there? Right, guys, what Greek letter is that? Huh? Yeah, rho, which stands for density. Yeah. So here, okay, let's get that down on the board. Okay, so you guys know Greek letter rho, which stands for density. They're telling you it's a ratio of what to what?
I swear.
Yeah, mass over volume. Right? Okay, so for example, this could be kilogram, this could be cubic meter, and this density could be in kilogram per cubic meter. Right? Or maybe it's grams per cubic centimeters or some version of that. Okay. All right, you guys got that? All right. How about one right beneath it? How do you think you read this? What do you think this says?
Pressure equals force over area.
Yeah, pressure is force per area. So pressure, capital P for pressure is force
So it's we got
per unit area. Okay. Which I think you guys saw last semester. Okay. Because guys, force could be in newtons, of course. Area could be in square meters. Okay. You guys, if you have 1 Newton acting on 1 square meter, that's also called 1 what? Yeah, Newton per square meter. It starts with the P. Pascal. Right. Guys, isn't one Pascal 1 Newton per square meter? Right. Hey guys, if I have a big old foam board that measures 1 meter wide and 1 meter long, like 1 by 1, okay, and I take this lab weight right here, 100 grams, weighs about 1 Newton. Is that true? Okay. And I stack this guy right here. Then this is putting some force on this area, and the pressure works out to be like this. Like that. Hey. How about you dive into a pool and you dive down to the bottom of the pool? Can you guys feel the pressure increasing the deeper you go?
Yes.
Right. And that's this one right here. Actually, these two kind of go hand in hand. Right. So this one says. Okay. So let's get a pool going.
These levels are so weird. So
big old swimming pool.
Your starting pressure plus health.
So this guy's gonna dive into the pool and go deeper. Right. Deeper it goes, the more pressure goes. Okay. So, guys, if the top of the pool is like level 0, and you go down to the pool some depth, I can call it H, right? some depth H. Okay. Okay, so that depth H, that's like right here. Okay, so that's that, right? What about the rest of these things? What do you guys think this stands for?
Initial pressure.
Yeah, initial pressure. So maybe that could be like the atmospheric pressure. Like if there's say his friend standing up here, like outside the pool, right? Maybe that could represent atmospheric pressure in this context, right? Like right now, we're all sitting in 1 atmosphere worth of pressure, right? That's pretty close to 100,000 pascals. Right? Right. And then the deeper you dive, okay, so this could be the pressure this guy feels at some depth, right? To move when he's like way down here. What do you guys think this stands for? This row?
Density.
Density. Density of what? Yeah, density of surrounding water in this case, right? Or in general, the fluid, right? Right. So if you had, say, like a tube of olive oil, maybe that could be the density of the olive oil. But in this case, maybe the water, if it's in a pool. Right? And of course, what does the G stand for? Gravity field. Right? Okay, so that's okay, right? Okay. You guys able to make sense of these? Now, right beneath this formula, is there any question about this formula? Right beneath that, there's a pretty similar one. It says pressure gauge. And that one's just called rho GH. Okay. And the idea is this. Like right now, we're all sitting in 1 atmosphere of pressure. That's a lot of pressure. It's like about 14, 15 pounds per square inch, 100,000 Newton per square meter. Right? It's an enormous amount. But it feels like normal, right? Feels normal. Okay. Now, if you were to dive down to the bottom of a swimming pool, see if you guys remember this from last semester. How deep do you have to dive to effectively double the atmosphere pressure? Okay, so 1 atmosphere this guy feels. How far down to get to 2 atmospheres?
Was it 32 feet?
Yeah, about 30 something feet or about 10.3 meters. Yeah. Okay, so metric about 10.3 meters. Okay. So if you dive down about 10.3 meters, okay. And what this expression here says is it's like the pressure beyond the normal atmospheric pressure. So if you're trying to compare two areas and you want to like subtract out the minimum pressure, right? Okay, well, if this guy is like starting at like some baseline value, we say like the increased pressure, just this bit right here would just be the rho GH. Okay, you guys can get that? Okay. So this guy at the bottom of this 10-meter deep swimming pool says like, oh, I feel like an additional pressure, or sorry, an additional atmosphere worth of pressure on me. That could be called gauge pressure. Okay. All right, you guys get that? Good. All right, now these. Like this. Okay. Okay. Guys, these last two right here. Right, this one, and this one. Okay. Those are basically these three right here: Archimedes principle, conservation of flow, and Bernoulli principle. Okay. Okay, and we're going to be looking at those today too. Okay. All right, so let's look at some of these here. And so start off real big picture. What are different states of matter out there? And so here's your main three, right? And these come with textbook definitions that work most of the time for most scenarios. Okay. So here, guys, think about this. Right, so solids and liquids are basically not compressible, right? So they have some defined volume, right? But a solid is usually something that has a defined shape, and a liquid does not. Liquid normally defines like it fills the container, something like that, right? Or in terms of shape, right? But it does have a fixed volume. Right? And when you get to a gas could have not necessarily a fixed shape, right? So you can stretch it and compress it, and you can change the pressure. Right? So a gas would have neither a fixed shape nor a fixed volume. Right? And for this last AP section, we're going to mostly just focus on liquids, although some of these equations and principles kind of apply to gases too, like Bernoulli principle. Right? You'll see some applications of that too. Right? Right, so from left to right, these are basically increasing energy or increasing temperature. There's a little more to it, but that's basically it. Right? Right, so if you keep eating a gas, make it a plasma. Do you guys see the fluorescent lights above us right now? Right, so that's an electric current running through a gas that's creating this excited state. It's called plasma, right? Where the electrons will separate from the atoms, right? If you keep heating up, right? Yeah, if you get to a really extreme case, like well, where the atoms themselves actually tear apart, right? So maybe you're looking like early universe or maybe supernova or something like that. You might get this really weird condition here. Okay? And what if you go really super cold? You get it's called a Bose-Einstein condensate. It's a weird state of matter. There's like weird quantum properties to it, but anyway, but our focus is pretty much just liquids, and there's so many gas applications for what we're doing. Okay. Right. Speaking of gases, I'm just gonna knock this one out. This is AP's not gonna ask you about this, but just want you guys to see this and think about this a little bit. Anyway, have you guys ever seen this before? Did you guys learn this maybe chemistry? How many guys learned this in chemistry? Oh yeah, awesome. Well, about half you guys have. Yeah. Okay. Yeah, because I ask my students every year, and it's like sometimes they do, sometimes they don't. Probably depends on the class and teacher. Okay. But say if you blow up a balloon, there's this relationship between what's the pressure inside the balloon, what's the volume of the balloon, and the temperature of the balloon. Those are the main three variables. Okay. Now, N represents, say, like the number of gas molecules inside. Right? Yeah, those it's for an ideal gas. Right? And R is some constant to tie all the numbers together. It depends what units you're working with. So if volume is in cubic meters and pressures in pascals and temperatures in Kelvin, then there's some particular value of R that goes for those numbers. If you switch your units and put volume in liters and so on, then there's a different value of R. It's just a number to tie everything together. Hey, here guys, let's navigate this a little bit. So to apply a little AP style thinking to this, like proportional thinking. Yeah, you do have to use an absolute temperature scale to do any equations on this. Okay? Because what if you have this balloon and you double the temperature, say from like 100 Kelvin to 200 Kelvin? What if you double the temperature and the pressure stays the same? What happens to the volume? It would also double, wouldn't it? Yeah. Because if you double the right side, you're going to double the left side. Is that? Okay. What if you have the temperature locked in place, so the temperature never changes, and you squeeze on the side of the balloon and make it half the volume? Guys, if the balloon is half the volume, what happens to the pressure inside? Yeah, double, because double times half would wash out, right? So if there's a fly flying around inside the balloon, you'll press the pressure. All right. Yeah, again, not gonna show up on the AP exam, but think about it a little bit. Okay. Oh, here we go. Here's density is mass per volume. Gotta have this one. Okay. So a good technique to get density is real classic. Goes back a long time. Is say you have some weird shaped object and you don't know what the density of it is, but maybe that could help you determine something about it, like its characteristics. Okay. So I want to know what material it's made out of, because I could look up on the periodic table and know what materials make, have what densities. Well, if you dunk it in water, you can see a volume change. Okay, if you put this on a scale, you can get its mass. So that's a quick way you can get densities. Just take that ratio of mass to volume. All right, for some object. All right. This next one. Here, yeah, I do have a few Paul Hewitts for you guys. So, whoops, that's the right. Yeah, here, I'm gonna play a few Paul Hewitts, and then we're gonna come back to some of these.
You got a drink, you want to cool it. Someone says, put an ice cube. Someone else says, look, crush the ice cube up, then put it in. It'll make the drink cold faster if you crush it up. Someone else says, it's the same amount of ice either way. Make no difference. You say, person next to you say, speculate, try it.
Yeah, okay, so mostly related to something else I was going to teach, but here. What physics principle do you think he's getting at? You said surface area, right? Like if you have a solid cube versus if you break it up, right? That would be really the difference between those two situations, right?
What's the answer again? How many people say it's the same amount? It's going to cool the same way either way. Make no difference. Hey, wait a minute though. Hey, wait a minute. No, if you crush the ice, you're going to get a whole lot of little pieces. And a whole lot of little pieces will have more combined area than the big piece. Crush it up. Crush it up. How many people say yeah? Yay. and you got a great big log and you want to light it with a match. Someone says, leave it in a great big log, it'll last longer. Say, yeah, but it won't light. Say, take your match. What do you do with a log? You shave off little pieces. And when you got little pieces, why will they catch fire quicker? More surface area, yeah. You got some steel wool sitting on your sink, and the steel wool gets rust out in 1 month, it's gone. But the same hunk of steel from which it was made will stay there for a year. How come the steel wool gets rusty and rusts away, and the hunk of steel like doesn't? More what? SA, surface area. Since the pressure is more against the bottom, what's to prevent that dam from scooting downstream? Especially when water seeps in here and you get these like little pebbles in here.
Guys, see if you guys follow what we just talked about a few minutes ago. Okay, so you guys see this big old dam right here, right? There's this big water reservoir behind it. Right? Suppose you dive down 10 meters and there's some amount of pressure. What if you go double the depth to 20 meters? Because if you go double the depth, what happens to the pressure? Does it also double? Yeah. So double the depth, double the pressure.
Ball bearings? Why couldn't that whole dam start from downstream? It could do that, couldn't it? But you can stop it. You know what you can do? You can put a heavy weight on the top. Tons of lead. You could squash it right down, and that heavy weight would scrunch the dam right in there, and it would be held secure. But there's a better way. You don't need the big chunk of lead. You know what you do? You design your dam like this. Why? Now the water's going to push like this. Which brings us up to a little rule. A fluid will always push in all directions against an object, but all those directions will conspire to give a perpendicular force, right angles. And so the weight of that water would hold that dam right against the bottom, just as a great big heavy lead weight on the top would.
Yeah, you guys hear what he just said? So the fluids will always push perpendicular to the surface that they act on. Right, so here, if I rewind a little bit, look before. Okay. We just had a vertical wall dam, right? Because that pressure is always pushing horizontal, right? But if he doesn't make it a vertical wall, right? Yes, so all this water is going to push always perpendicular to that surface.
Right? Weight on the top wood. So pressure pushes in all directions, but the force of that pressure always turns out to be perpendicular to the surface upon which it acts. You know that's true because if you take a bucket and you put it in the water and you punch some holes in, but no matter where you put the holes, when you put this down here, the water will spurt in. If the hole's here and you're dunking under the water, it'll spurt in that way. If the hole's on the bottom, it'll spurt straight up.
Yeah. Okay, so you guys know that force is a vector, right? Force is a vector, which means it has a direction associated with it. Right? What do you guys think pressure is? Do you think pressure is a vector or a scalar? Yeah, a scalar. It is a scalar, right? So there's not really a direction associated with pressure, right? But the resulting force, that's what I said. The resulting force is always perpendicular to the surface.
Put an angle like that, it'll spurt like that. It will always spurt perpendicular to the surface. It acts in all directions. Water pressure. Interesting stuff. There's the rock under the water. There's some pressure against the bottom. That pressure pushes against the bottom with a force. There's pressure at the top. It pushes down with a force. Why am I making this arrow not so long as this arrow? This part's deeper. This part's deeper. That means there's more pressure. That means the water's forcing up against the bottom harder than at the top. Why am I making these arrows between the light size of that and that? Why? In fact, I can ask you a question, you can answer it. Why is it when you submerge something in the water, it doesn't start to just nudge sideways? You can see it. Check your neighbor. Okay, gang, let's look at it. We can see the rock is not buoyed sideways. Why? Because these forces are the same. And the force underneath is always going to be greater than the force on the top because it's deeper.
Right, he's trying to build up to something. It's going to lead to one more I'm going to show you guys. Right, which is, why do you float in a pool? Or why is it that you can throw something in water and it tends to want to float? Or if it does sink, like if you put a rock on a scale and it weighed, say, like 10 newtons, and you put the scale at the bottom of a swimming pool, and you put that rock on the scale, would it still read 10 newtons? No, it would read less, maybe only 7 or 8 newtons, right? Okay, so it's something about the water is trying to force it upward, right? Trying to force it upward. Right? If it's light enough, if it's like small density enough, it'll even float. Right? So why does that force act upward? And what he's showing here is that the deeper you go, the more the pressure is. And since objects are three-dimensional, that there's always going to be more pressure and therefore more force on the bottom of the object compared to the top, right? Okay, so that's why there's always an upward acting force, right? So one more is like, what is the magnitude of that force? And that's going to be related to Archimedes' principle.
What I'm gonna do. What I hope to do. Is I'm gonna dunk this in the water. And when I do that, this weight reading will go down, yeah?
All right, so how much does that weigh right now? Yeah, 10 newtons, 10 newtons.
And I can kind of show you over here. The weight reading does go down. Would you say this? That
Went down to approximately what? Yeah, 6 newtons, right? Therefore, what do you think is the buoyant force that's acting on it? Yeah, 4 newtons, right? Okay. If you drew a free body diagram, I'd say, okay, there's 10 newtons of weight acting down. There's 4 newtons buoyant force acting up. And what other force is there? 6 newtons from the string, right? Because the scale is showing the string tension. It's really what that scale is showing, right?
loss of weight was equal to the support force. And that support force, we have a name for it, begins with BF. Buoyant force, okay? So the buoyant force can be seen by the loss of weight. Can't read that now, but read it now. Read it now, subtract the two, there's a buoyant force, yeah? I'm gonna do it over here in this overflow can, but I'm gonna catch the water that's displaced. And I'm gonna weigh it. Whoops. This is not gonna be perfectly accurate.
Okay, so if you missed it, some water was spilling out already, so might not be 100% accurate.
Okay, but note now what the reading is of just holding, it looks like a little bit more than 1 Newton.
So right now, this empty beaker weighs about 1 Newton. Okay, weighs about 1 Newton empty.
Holding up the empty cup. And I dunk this in. This is losing weight, yeah? It's because I'm displacing more and more water. There, now this has lost all the weight it can lose. This is still catching water.
Okay, so it's got a little bit more water to catch. And again, okay. Guys, is this needle getting pretty close up to about 5?
Yep.
Right. And the empty container was 1. So how many newtons did this one pick up? 4. This one picked up 4 newtons. This one over here lost 4 newtons. You guys see it's the same? It's the same, right? So what he's trying to show is that if something's submerged in water, in this case, that buoyant force that's pushing up on this weight, right, the magnitude of that force, in this case 4 newtons, is exactly equal to the weight of the water displaced, right? The weight of the displaced water.
I want you to compare how much weight did this lose, the suspended weight, and how much weight did this gain? Do you see that they're the same? And that brings us to a very important rule with fluids. And that's this, that the buoyant force that acts on a submerged object is numerically equal to the weight of fluid displaced by the object. Okay? I didn't say the buoyant force is equal to the weight of the object over here. No, it's the buoyant force is equal to the weight of fluid, in this case, water displaced by the object. Okay? We see that? That's called Archimedes' principle.
All right, and that's what this one is right here. Right, so the same experiment, maybe different materials this made out of, because the numbers are a little bit different, but same idea, right? And so this was just hanging in the air, got 2 forces, weight down, tension up, 10, 10, right, scale reach 10 newtons, right? Okay, you submerge this in water, and maybe catch all the water in this overflow can here, right? And if the scale rating jumps from 10 down to 7, right? Now the string tension is only 7, right? But Earth's still pulling on it down with 10 newtons, right? This upward acting buoyant force is equal to the weight of the water that was just displaced, which is 3 newtons. Right? So 7 and 3 up, balanced with the 10 down. Okay? Right, so the buoyant force is equivalent to the weight of fluid displaced. Okay. Now, let's go in detail here. Okay. Because weight of something is mass times gravity field, right? That's weight. Let's say weight is mass times gravity field. But let's substitute out the mass of something in terms of its density. Okay, so do you guys remember density is mass per what? Volume, mass per volume. Okay. So can I rearrange that and solve for mass and make it density times volume? Is that okay? Okay. So this mass could be density. We're talking about the density of the fluid, the density of the water in this case. Okay. Times the volume displaced. So this is water. This is displaced. Okay. And then G. Okay. This would. Okay. This is the weight of the displaced fluid in this case, okay, which is also equal to the buoyant force. Okay, that's Archimedes' principle. Okay. All right, so that's what we got right there. Right. And so this buoyant force, this upward acting buoyant force, it's always going to push up. Right? It's equal to the density of the surrounding fluid, which is oftentimes water, times the displaced volume. And if the object itself is completely submerged, then the displaced volume would be the volume of the object. Okay. But that's not always the case, because like, what if you have a boat that's floating on the surface? Because if it's a boat floating on the surface, the displaced volume would have to be less than the volume of the boat, wouldn't it? Okay, so we're just talking about how much water is being pushed out of the way, really. Okay. And then we got the gravity field. Okay. All right. And you guys see that is the same thing as this one right here. It says F sub B. What do you think B stands for? Buoyant. Yeah, guys, that's buoyant force. We got the density of what is this, guys? Guys, is this the density of the object submerged or the density of surrounding fluid? Density of surrounding fluid. Right? Right. And then volume displaced and then gravity field. Okay, so that's Archimedes' principle. All right, you guys good with Archimedes? This good? All right. Okay, so here I got two similar concepts and similar looking formulas, a little bit different. Okay, so guys, what is force measured in again? Newtons. What is pressure measured in? Pascals, which is Newton per square meter. Okay. Okay. So here's Bernoulli principle. Right, so the buoyant force equal to density of the surrounding fluid, the displaced volume. So if there's this ice cube that's floating, then only the part that's pushing water out of the way, that's that volume right there. Okay. Not the entire ice cube, just the displaced water part. Okay. And then gravity field. Okay. Now that's a force. That's a force measured in newtons, which is a vector quantity, acts upward. Okay. No, it's different from saying what's the pressure. Oh, look, and I got kind of what Paul Hewitt was showing, where if objects are three-dimensional, then there's more pressure acting on the bottom of the object compared to the top. Okay. But if you had, say, a diver and you wanted to say, treat the diver as like a point or something, you just say like, oh, he's like so many meters deep. You know, do that too. Okay. And so how much pressure is there something? Right. So it's rho GH, where H is the depth. Okay. Now again, really similar looking formulas. They both got the density of the surrounding fluid, so that's the same. They both got this gravity field of the planet, so that's the same. Okay. What's different is for force you need the volume that's displaced, and for pressure you just need to know how deep you are. Okay. Again, that's related to these two guys right here. Okay. Right, so I guess sort of all three of those are related to it's on this poster. Okay. You guys have that? Right, here's a classic physics question: is if you see an iceberg floating in the ocean, what percent is above the water line, or what percent is submerged? Okay, well, it has to do with the densities, the relative densities of the ice in the water. Okay. So guys, if you have a little tiny ice cube, and you have a big old iceberg, do you think the percentages are the same? Like the percent submerged is still the same? Right. Right. So here, I'll walk you guys through step by step. Okay. So let's start with free body diagram here. So I got the weight of the iceberg trying to pull it down to the bottom of the ocean, and the buoyant force keeping it up. Okay. So if those are going to zero out, that looks like force equilibrium, right? Force equilibrium is just floating there. Okay. Okay, so these forces must be the same magnitude, one up, one down. Okay. Now the buoyant force, here's Archimedes' principle, is rho VG. Okay. Density of the, guys, what density is this? Is this the ice or the surrounding water? Water, because we're talking about the buoyant force. And which volume is this? Is this the entire ice cube or is this just the submerged part? Yeah, just the submerged part. This is just placed in the water. Okay, and we got gravity field. Okay. Okay. But on the side of the weight, okay, this weight that's trying to pull this entire iceberg down to the bottom of the ocean. Well, I know the mass of the ice is the density of the ice times the volume of the entire. Well, guys, which volume is this? Is this the volume of what? Yeah, the entire cube of ice, including the part that's above the water. Okay. And then okay, then we got gravity field again. Guys, which variable cancels out at that point? Yeah, the gravity field of the planet. So, guys, if you took this whole system to Mars, and you had like a big tub of water in Mars, would the same proportion of this ice cube still float above the waterline? Yeah, because gravity field cancels out. Now, you need gravity to make this happen, otherwise everything is floating around. Once you have gravity, it doesn't matter how much gravity. All right. So then what you can do is you can rearrange the variables that are remaining to get proportions. Guys, notice this is a proportional answer because it doesn't matter how big the iceberg is. And so the displaced volume compared to the entire iceberg. Okay. Now, guys, this fraction, what is this set up to solve? Is this the proportion that's above the waterline or the proportion that's below the waterline? Below, yeah. Okay. It's this volume down here compared to the entire iceberg. Okay. So it's the percent that's submerged. And that turns out to be the same as the ratio of the densities of ice compared to water. Okay. Okay. Now, guys, what is the density of fresh water?
A great question.
It's what? It's exactly 1 kilogram per cubic meter. Or sorry, no, sorry, that's not true. Sorry, 1,000 kilogram per cubic meter. That's what I meant to say. Okay. Guys, fresh water is exactly 1,000 kilogram per cubic meter. Okay. Now, ice is approximately. I'm going to round a little bit. Guys, ice is approximately 900 kilogram per cubic meter. Okay. So, guys, what is 900 compared to 1,000? Is that called what percent? 90%. 90%. Okay. So typically, when you see ice floating in water, what percent is below the water? 90%. What percent would be above the water? 10%. Okay. Okay. Of course, if you had hard numbers, you could throw some numbers in there too. All right. Pascal's principle. Oftentimes worded like this. Pressure is transmitted. Here, guys, look here. Take it up. Pressure is transmitted undiminished throughout a fluid. So if you have here, I'll draw you guys a wackier picture than that. Suppose you have some like weird underwater cave system, right? And it's like does maybe something like this, and then here's the water level here, and there's another place over here. Okay. Maybe here's the ground. It's got some trees right here. Right, people walking around. Okay. Right, so somebody looks in here and says, "Hey, it looks like this lake opens up, and there's maybe some kind of underground cave or something." Right? Hey guys, are these water levels the same? Show of hands. How many of you guys think these water levels have to be the same? Yeah, they sure do. Let's see if I drew that about right. Yeah, guys, those water levels have to be the same. They have to be the same. That's related to Pascal's principle. Okay. And what if we send a diver down here? And he goes so deep. Maybe it's like 10 meters deep. H equals 10 meters. Okay. And we send a diver down on this side, and he also goes down a depth of 10 meters. Is the pressure the same here as it is here? Okay. Is the pressure the same here as it is here? Yeah. So equal. Are there always going to be equal pressures at equal depths? As long as the water is not flowing, that'll be true. If it's just the stagnant water, yeah, then equal depths is going to be equal pressures, and the water level has to be the same everywhere on top. Okay, that's all embedded in this Pascal's principle, right? Right now, this poster actually shows well, something else interesting going on. I got a hydraulic lift going on. Hydraulic lift. Okay? So I see this hydraulic fluid. I know the pressure's the same everywhere, especially equal depth, but there's not a whole lot of depth to this. So let's just say it's basically the same pressure everywhere. Okay. So that means the pressure on the left side has to be the pressure on the right side. Okay, so it's equal pressure everywhere. But you guys know pressure is force per unit area, right? You guys know that? Okay. But as what if I have different sized pistons? I've got a small area piston on the left side and a large area piston on the right side. Well, guys, these are different areas, different cross-sectional areas, but they're acting over on the fluid. It's the same pressure. Okay. That means that there's different what acting on each piston. Different forces. Yeah. So maybe with the small input force on the small area piston, you can get some pressure that ends up being the same pressure on the other side. And you can lift something very heavy on the other side. So a large force on a large area would be the same ratio. Okay. It's called a hydraulic lift. Okay. Guys, does this kind of look like that pulley system over there? You guys remember pulley systems? You guys built some pulley systems that gave you a mechanical advantage. You guys remember that? Okay. Hey, I think this is really analogous to that, isn't it? Okay. Because with both the pulley system or the hydraulic lift, you can lift something very heavy with a small input force. Either one, you can do that. Is that true? Okay. But I remember with the pulley system, the catch was you had to pull lots and lots of string, and the heavy weight lifted up just a little bit at a time. Is there something similar going on here? What do you think is sort of the equivalent like trade-off here? Yeah, you guys see that? You guys see, like if you compare the volumes of liquid on both sides, right, you would be displacing an equal amount of volume also. And what that means is you have to push a long distance on the left side, and the car on the right side in this case lifts very, very slowly. Okay? Okay, so you can lift something very heavy, it's just a little bit at a time. Okay. So hydraulic lift.
YouTube.
Yeah, YouTube. Alright, so what if you have this tube? Now I got this one open at to the atmosphere at both ends. There's different variations on this, but this is a pretty fundamental approach. Okay, I got all these different liquids. Maybe this blue liquid might be like water, and maybe these other three liquids are different types of oil that are going to float on the water, but maybe they have each their own individual densities. Like maybe the water could be 1 gram per cubic centimeter, and maybe this green is like 0.9, and this yellow is like 0.7, and this gray is like 0.8. I don't know, whatever the numbers could be. Okay, so so isn't it true that the smaller density liquid always wants to float to the top, and the larger density wants to float to the bottom? Okay, so it'll separate out like that. Okay. But then if you look at the height levels on these, well, so these heights are at all different locations. Okay. And the principle here, leading us to this this formula out here, maybe I'll cover this up and see if you guys can reconstruct this, is guys, does there have to be equal pressure along this line, all along the bottom? Is there equal pressure? Yeah, we just talked about that with that cave system, right? You guys remember this cave system we were going through? There was equal pressure at equal depths. Okay. And again, we're not to flowing water yet. Right? So all these fluids are just stagnant. Yeah, you just turn it right. And so equal pressure right here on the left side and the right side. Well, if you go up the arms right here, guys, we're at right here and right here. Again, equal depths right here and here. Is this still equal pressure right here? How many guys say yes, it's equal pressure right here? Show of hands. Yeah. Right. Because we're still inside this blue fluid. Let's call it water. Okay. So it's still the same. Okay. How about up to right here? Is it still equal pressure? Who says it's still equal pressure? Yeah, sure is. Okay. Okay. Now, guys, if I go to here, do you think this is equal pressure right here and here? No, probably not. No, I wouldn't say it's straight anymore. Right. Now, maybe one point of evidence for that is if you go up to like here, like I see it like right at this line. Now, are we basically atmospheric pressure right here? Right, but that's not true here. This would be a little bit less or a little bit more than atmospheric pressure. It has to be a little bit more because it's the whole atmosphere plus this little bit of this gold liquid right here. Right, atmospheric pressure you don't reach to the top right here. Okay, is it? Okay, all right. So looks like here and here the pressure are the same, and here they're both atmospheric pressure. So that's also the same. Okay? But there's a different journey on the left arm and the right arm of this U-tube. Right. And so let's set an equivalence principle this point to this point. Right, you guys ready to do that? Now, you guys remember in general, pressure is density of the fluid times the gravity field times the depth. H could be depth. Right, capital P is pressure. Okay. Okay. Rho is density, G is gravity field. This is the press out. Density. Okay. Is that okay? Okay, that's far. Okay. Alright. And I'm covered up a formula in the school box right here, but I want to see if you guys can reconstruct this because if you can apply some critical thinking and reconstruct this formula, then you know it, and you know that you know it, and you'll be able to figure out from scratch. Okay. Okay. I mean, that's always been a big thing in this class, right? Like, if you know some basic principles, you can usually figure out everything that's going on, right? You don't have to memorize like a billion details, but if you know some guiding principles. Okay. All right, so let's say the pressure on the left side equals the pressure on the right side, right here. So I'll say P left equals P right. So I'm talking about right here and right here. So go ahead, guys, in your notes, see if you can reconstruct what I'm covering up with my paper.
I got you.
So the left pressure equals the right pressure. Okay, go ahead.
I did.
You know what you're doing, go ahead. If you need a hint, I think the left side pressure story is this rho GH and this rho GH and this rho GH, and the atmosphere is sitting above that. And the right side of the story, we got this rho GH and this rho GH and this rho GH, and the atmosphere is sitting above that, also push it down. Okay? Okay. All right, did you guys put it all together?
Yeah.
Let's get that. Okay. So here's how this is finished right here. Okay. And so both the left side and the right side have the atmosphere pushing above, okay, which can effectively cancel out. Okay. We got this rho GH dot bit right here, which is the same for this part of the journey for both left, right. So that can cancel out too. Okay. And then, on the left side, I got this rho 1 GH1, this rho 2 GH2. Okay. And on the right side, I got this green and this gold, rho GH3 and rho GH4. Okay. Again, each of these fluids can have their own individual density. That's why I got different subscripts on these rows. Okay. There's some individual height of each of those. Okay. Oh, notice they're all the same gravity field though. So guys, if I took this U-tube with these exact fluids in it to Mars, would they settle at exactly the same locations? Yeah, they sure would. Because the strength of the gravity field doesn't matter. Okay, you guys good there? Alright, so yeah, I've seen different variations on this. Here's one variation. What if you close one side so it's no longer open to the atmosphere? Okay. Could you have some lock-in pressure right here? Okay. And oftentimes you even see where maybe they vacuum this out and they just have a vacuum here. Okay. That's a common setup too. Okay. Guys, so what if you did have a vacuum here and you let's say like poured in some water? Okay. Do you think the atmosphere on the right side would push the water up some height? Okay. How high could the water be pushed up if this side is closed and there's a perfect vacuum over here?
Is it like one atmosphere?
Okay. Okay. Yeah. So one atmosphere worth of pressure is pushing on the right side. There's a vacuum on the left side. So what's this height differential for water? We said it earlier today. About 30 something feet, about 10.3 meters, right?
Yes.
10.3 meters. Yeah. Okay. Now, guys, 10.3 meters, that's pretty tall. That's probably like about as tall as the skull. So, hundreds of years ago, they didn't use water. They like to use mercury because mercury is so dense, so heavy. Guess how high mercury goes approximately? It's about 76 centimeters. So about 3/4 of a meter thick, which is a lot more manageable. That's of course in 1 Earth atmosphere. So a little bit different equation setup right here. All right. Okay. No, we only got about a minute left. So I was hoping to get the conservation of flow and Bernoulli push flow. I'm gonna have to save these for next time. Yeah. Up there. All right. So next time, gonna be conservation of flow and Bernoulli.